Hello everyone, today I'd like to introduce our paper named Hierarchical Code Decomposition in Parallel from Construction to Subgraph Search. I'm Deming Chu from the University of New South Wales. Code decomposition is a powerful tool in network analysis, and it can decompose a graph into layers. There are several limitations of code decomposition. The first is that the connectivity of k-cores is lost. For example, here we have two different k-cores, but the vertices in them are viewed as the same in code decomposition. And then the second problem is that the containment of k-cores is lost. We have this containment relationship here, but it is not stored in code decomposition. So therefore, the first problem we want to study is hierarchical code decomposition, which formalizes the connectivity and the containment of different k-cores. And it can be stored in O(n) space, where n is the number of vertices. So here is an example. We prove that the problem is p-complete, which means that it's inherently sequential. Despite this negative result, we design a near linear walk parallel algorithm for it. Here is the applications of ICDE, so we can apply it to cohesive subgraph search and use it to find inferential k-core, attributed k-core, and densest subgraph. And also in user engagement analysis, it can give more accurate predictions and code decomposition. We can also use it to visualize the internet, biology, and brain networks. The next problem is subgraph search on ICDE. So we want to find high-quality subgraphs on ICDE. And we use community scoring matrix to evaluate subgraph quality. So for example, average degree and clustering coefficient. We have many k-cores in this ICDE, and we want to evaluate all of them. We design walk coefficient parallel algorithm for it. So here, walk coefficient means that the number of steps matches the best sequential time complexity. For the application of subgraph search, our solution is the state-of-the-art approximate solution for densest subgraph. And also our solution can be a potential pruning strategy for maximum click. It can also be applied to size-constrained k-core. Next, I will define the problems. So k-core is the maximum connected subgraph, where each node has at least k neighbors, and coordinates is the larger case such that the node is in the k-core. Using this property, we can divide the whole graph into 3 layers with coordinates 3 to 1. Then it's for hierarchical code decomposition. So k-core tree node Ti stores the vertices with coordinates k in a k-core Si. So here in this 2 core, we have green vertices coordinates 2, and we store them in the tree node. We see that T1 is the parent of T2 if this S2 is containing S1 and the K is just smaller, and also we don't have any K prime core S prime such that S prime contains S2 and is contained by S1, so that it's direct parent. And ICDE is to find all k-core tree nodes and their parent tree node. Next, I will talk about community scoring matrix. So first is primary value for a subgraph S, because most matrices are based on primary values, and we have the number of nodes, edges, boundary edges, triangles, and triplets. So based on those primary values, we can define those matrices to measure community quality. We divide the matrix into two categories, type A and type B. And type B is based on higher order motifs, triangles, and triplets. So here is the second problem. Given a graph and a community scoring matrix Q, we want to find the K-core with the highest score with respect to Q among all K-cores, and all those K-cores can be searched on the ICDE. Next, I will talk about the parallel construction of ICDE. So here is the existing work. LSCPS is the state-of-the-art serial algorithm, and it runs in OM time, where M is the number of edges. We found that in this algorithm, concurrent visits of vertices will lead to inconsistent priority ordering and results, so it cannot be parallelized. And then other serial methods are much slower. And here is our conclusion. Existing works are hard to parallelize. Divide and conquer method is infeasible according to our experiments. Therefore, we design a new union find based solution. Here's the intuition. We add vertices to union find in decreasing coordinates, and meanwhile we build HCD from bottom to up. We use pivot to identify tree node and its parent. Here is the definition of pivot. Vertex run is to sort nodes by coordinates and break tie by ID, and pivot is the vertex with the lowest vertex rank in a subgraph. So therefore, pivot can uniquely identify K-core and its tree node, so we can find that this pivot is unique and it's also in the K-core tree node, and therefore we can use it to identify both the K-core and its tree node. There are two usages. The first is that we can use it to group vertices. So use this pivot, we can identify different connected components and group them into tree nodes. The second is that we can use it to find parents. So after we adding those green vertices, the pivot change from the old one to new one, and there will be a parent-child relationship between the tree node represented by those pivots, like this. Here is our solution. So we have 4 steps. We're doing it in decreasing K, from K max down to 0. So here we have 2 tree nodes here, and we have those 3 cores, and we want to add those green vertices coordinates to the graph. The first thing we need to do is that we visit green vertices neighbor and identify K prime core that will union with green vertices. So here K prime is larger than K, and we got 2 K prime core tree node here. We store them. And then we union all those green vertices with their neighbors if the coordinates is equal or larger. And then we can find that the pivot is changed from those old one to new one. And then using those new pivots, we can group green vertices into tree node and construct this new tree node. And then after that, if it's in the same connected component, and then the tree node containing those new pivots and old pivots, they would have parent-child relationship, and we can find those relationship here and store them. We also designed a data structure called union find with pivot based on weight-free union find, and it is suitable for parallel algorithm. It maintains the pivot of connected components in the data structure, and this is the time complexity. N is the number of vertices, P is the number of threads, M is the number of operations, and alpha N is reverse a command function, and it is no more than 4 for any practical N. F is the failures in weight-free union find, and this is the dominant term, which is near linear. And we also design parallel vertex rank computation. So for every thread, we just distributed all the vertices in decreasing ID, and then group vertices by coordinates, and then place back into array and obtain vertex rank. Here is the analysis. So we prove that the problem is P-complete, or in other words, inherently sequential. The data structure can be stored in ON space, and this is the time complexity of constructing it. And the time is near linear work, and it is also the cost of uniting all edges in weight-free union find. And then we talk about parallel subgraph search on HCDE. Here is the existing works of subgraph search. The first is BKS, and it computes in decreasing coordinates, and it relies on the results of larger coordinates. And the pre-processing in this algorithm is inefficient to parallelize, so this is the limitation, and we want to overcome them. Therefore, in our algorithm, we design a vertex-centric solution, and there is no dependency on data, and we design a novel pre-processing. Overall, our algorithm is efficient to parallelize. Here is our solution. We first compute HCDE, then do pre-processing, then do score computation, and finally output the best K-core. So for pre-processing, we compute for every vertex the number of neighbors such that its coordinates is larger, equal, and for last one we just degree minus those two, then we got the least one. Then I will talk about step 3, the intuition of score computation on HCDE. So given a K-core, we can reconstruct it by the K-core tree node and its offsprings. So for primary value, for example, the number of edges, we can first sum up the primary value of all sons, and then we just add the contribution of the K-core tree node for all those vertices. We compute them. Then we can get the primary value of the K-core, and then using that we can finally get the score. So here is an example with type A. We want to get average degree, so it's about the number of vertices and edges. For every vertex in parallel, we compute this number of vertices and edges, and this can be helped by pre-processing. And then we sum up them into tree nodes here. And then we do bottom-up summation here. So this one is the sum of these three. So that we get the primary values of K-cores, and then we can obtain the score of K-cores. We just divide them and times 2. And then for type B score computation, it's similar but more complex compared with type A. For triangle, we use lower degree endpoint to check triangle existence. And for triplet, we count triplets based on the coordinates of neighbors. So, and then after score computation, we just output the K-core with the highest score. So overall, we need pre-processing of OM work. Work is the number of steps. Then for score computation, we need ON work for type A and OM to the 1.5 work for type B. Score computation is work efficient. That means the step matches the best serial time complexity. Next, I will talk about the experiments. So we use 10 public networks and we have up to 100 million nodes and 4 billion edges. We use a quad-core up to 40-thread Linux server with 128 gigabytes of memory. For HCD construction, the serial version of our algorithm is a little bit faster than the state-of-art, and when 40 cores are used, we are 10 times faster on small networks and 15 to 20 times faster on larger networks. So our algorithm is significantly faster than LCPS, the state-of-art. Then we let LB be the lower bound cost of union find based method. We can find that LB is about half of the cost of our method when 1 core is used or 40 cores are used. So our PHCD is close to the lower bound. And also we let RC be an algorithm, and it is required in divide and conquer method. We can find this number is very large here, so therefore divide and conquer paradigm is inefficient in building HCD. Then is subgraph search. So when 40 cores are used for type A score computation, we are 30 to 40 times faster for small networks, 50 times faster for larger network, and for type B, both of them is 20 times faster, and it's significantly faster than BKS. Then it's for the applications on density subgraph. So it is to find the subgraph with the highest average degree. We compare the algorithm to a reasoned approximate solution and the state-of-art serial solution, and our solution PBKSD is that our subgraph search of the K-core with the highest average degree. So we have 3 conclusions here. First is that the algorithm is a half approximate solution. Second, that our algorithm outputs denser subgraphs than other algorithms. And then it is 10 times faster than algorithms. So therefore it outperforms existing solutions. The next application is maximum click, and it is to find the largest subgraph where every pair of nodes is adjacent. We still use PBKSD and we let S star be the output of our algorithm. On the left side, it means that S star contains the maximum click, and we find that our output graph contains maximum click in 7 out of 10 datasets, and the size of it is on average 1% of the graph. Therefore, our algorithm can be a potential pruning strategy for maximum click. Then we come to the conclusion. For parallel HCD construction, we prove that the problem is P-complete. And we designed the first parallel algorithm, and it has near linear work. For subgraph search, we designed the first parallel algorithm, and we find that its score computation is work efficient. We also find the problem is useful in related problems. We design applications on approximate density subgraph and maximum click, and the runtime is much faster than existing works. That's all. Thank you.